Okay, it is a pleasure to be giving this talk today. In thinking about the talks, the invitations to accept, one of the things that really struck me about this invitation was the nice connection that I have personally with Geneva, as this is where my father grew up, and he attended the University of Geneva. So I have, I think, a very nice personal connection to CERN. Today, I would like to share with you the work that I've been doing for the last 25 years at Keck Observatory, where the initial question was, is there a supermassive black hole? And by that question, we were really after trying to demonstrate the existence of supermassive black holes in the universe. And what I hope to convince you by the end of today's talk is that we have dramatically improved the case for the existence of supermassive black holes, moving it from a possibility to a certainty, and created a wonderful laboratory through this discovery for understanding both the physics and astrophysics of black holes. So in particular, understanding how gravity works near a supermassive black hole, as well as the astrophysical role that supermassive black holes play in the formation and evolution of galaxies. Okay, so to begin with, let's think a little bit about, or just review where we were 25 years ago. So if we think about the case for black holes, certainly the case for stellar mass black holes, which were thought of from a theoretical point of view, and then discovered observationally. And today we have exquisite evidence for the existence of the stellar mass black holes through LIGO and Virgo. So it's a case where we thought of the evolutionary case for the massive stars in our galaxy, and the end product should be stellar mass black hole of roughly 10 or so times the mass of the sun. The case for the supermassive black holes was very different because they weren't anticipated from a theoretical point of view, but rather it was observations that pointed the way to these much more massive objects that are thought to be on the order of 1 million to 1 billion times the mass of the sun. And it was observations of galaxies known as active galactic nuclei. And these galaxies have a tremendous amount of energy coming out from their centers, as this picture that's at radio wavelengths shows. So most of the galaxy is contained on very small scales at the center of the image, but emanating out from the core are these huge jets of emission. We can see how fast and measure how fast they're moving, so we know there's a tremendous amount of kinetic energy, suggesting that there's a very powerful central engine at the middle of the galaxy. In addition to that, the emission at the center is unlike anything that's produced by stars or gas. So it was suggested that supermassive black holes are the central engine of these very active galaxies, which comprise roughly 10% of all galaxies. So 50 years ago, in the 1970s, which is now 50 years ago, 30 years ago at the start of this experiment, it was suggested that perhaps all galaxies harbor these supermassive black holes, and in these that galaxies that are not active, the supermassive black holes are simply quiet because they don't have matter accreting onto them, so that they're in a sense stealth black holes. So this is a galaxy that looks very much like our sun, our galaxy if we could get outside and look back. Our sun is roughly halfway out in one of these, in something that looks like one of these spiral arms. And in fact, our galaxy presents the best case to look for supermassive black holes because it's the closest galaxy we have the possibility of studying. The next closest galaxy is 100 times further away. Now, the challenge with our own galaxy is that we live within it. So this is a picture of the plane of the Milky Way. So the Milky Way is a flattened disc-like structure. Because we live halfway out and are looking towards the center of the galaxy, we have to look through the plane of the galaxy. And one of the challenges, so the pro is that we're close to the center of the galaxy, but the con is that we have to look through a tremendous amount of dust to detect what's happening at the center of the galaxy. And as this picture shows, well, there's a lot of stars that we can see above and below the galactic plane. In the plane itself is quite obscured because of the dust. So the dust absorbs very effectively photons that have wavelengths roughly the size of the dust particle. So it's very effective at blocking optical light, which is, of course, where this picture is taken. So only 1 out of every 10 billion photons emitted from the center of the galaxy makes it to us, meaning that it's effectively invisible at optical wavelengths. But if we go longward of the optical into the near infrared, and by near infrared, I mean roughly 1 to 5 microns, and in particular 2 microns, 1 out of every 10 photons emitted from the center of the galaxy makes it to us. So we can see what's happening at the center of the galaxy. And in fact, key to this experiment, or why it was possible to begin this work roughly 25 years ago, was the advances that were made in infrared detector technology. So that's a key development that was that enabled this work. Now, the objective of the work was to detect the supermassive black hole through its gravitational influence on the stars around it. So by simple freshman physics, we all know that the orbits of stars for a spherically symmetric mass distribution should tell you the mass that's enclosed within their orbit, simply through Kepler's laws. So at the beginning of this experiment, it's interesting to realize that what we were after, and this is true for both groups that started out at this time, we were thinking that we were going to do this from a statistical point of view, which is to measure the average speeds or velocities of the stars, and to argue that the dispersion of those velocities give you the central mass. So that's a standard technique used in astrophysics to measure the mass distributions, is to go after velocities. So we were after velocities in the plane of the sky. And clearly the goal is to be able to detect the stars that are as close to the center of the galaxy as possible, because the demonstration of a black hole is to confine the mass to within a small region. In particular, you're after showing that there's a mass within the Schwarzschild radius. That would be the ultimate test. So you're after the stars that are as close to the heart of the galaxy as you can possibly detect. So in fact, our work has been done with the Keck telescopes. The Keck telescopes were just opening at the time I began my faculty position. So in fact, this was really why I wanted to work at UCLA, was to gain access to these fabulous facilities. They're the largest telescopes that are working in the world today at optical and infrared wavelengths. So we characterize telescopes by the diameter of the primary mirror. So each one of these telescopes is 10 meters in diameter, which is effectively the width of a tennis court. So in fact, there was tremendous technical innovation that allowed these telescopes to be built. So this is the first successful departure from single mirrors built to create the primary mirror, to go to segmented architecture. So each telescope is composed, the primary mirror is composed of 36 hexagonal segments to achieve the 10 meter, or effectively, actually it goes all the way out to 11 meters at the corners. Okay, so telescopes in principle can allow you to see things that are very faint because they're large apertures, but in principle you can see higher detail. So the diffraction limit of a telescope increases as you go to larger telescope diameter. So in principle, you can see smaller angular resolution. You have higher angular resolution as you go to larger and larger telescopes. But of course, the problem for ground-based telescopes is the atmosphere. It's great for us. It allows us to survive here on Earth, but it is a total headache if you want to image astrophysical sources. So here's, actually, this is some of our first data sets that we took on the center of the galaxy. Each exposure is 1/10 of a second. And it very nicely demonstrates the issues that we faced with the atmosphere. So if there's no atmosphere, there's roughly 5 bright stars that you can see dancing around on the screen. Each star would be the size of the smallest structures that you're seeing, known as a speckle, and they would be rock solid. So it's the atmosphere that creates this effective bug splat pattern that we're watching dance around. So it's actually, to me, it's actually rather amazing if you think about it. Here's this light, these photons that have been traveling from the center of the galaxy for the last 26,000 light years. And in the last 30 microseconds, they hit the top of the atmosphere and get completely distorted. So the challenge, or the challenge that I've been interested in for most of my professional life, is to think about how do we overcome the blurring effects of the Earth's atmosphere so that we can achieve the true scientific potential of these really large ground-based telescopes. Now, there are a lot of solutions to this. One is you put up a telescope above the atmosphere, and that certainly solves the problem. So this is the power of Hubble Space Telescope. Now, Hubble Space Telescope has a mirror of 2.4 meters in diameter. So in fact, it's a relatively small, but very effective facility. The kind of work that I'm doing at the center of the galaxy, the scientific power or improvements that you get from getting to the resolution theoretically offered by these telescopes goes as the diameter to the 4th power. So it's a very strong dependence with diameter. So Keck telescope's 4 times larger, so you have 4 to the 4. So you're really talking about more than a factor of 100 improvement, at least. And in fact, you'll see that this gets highly leveraged as that resolution allows you to approach the problem from a fundamental different perspective. Okay, so over the last 20 years, 2 decades, there's been incredible progress made with our ability to get these high resolution images. So it's useful to keep in mind as we think about the work that time definitely helps, because you're measuring the orbital evolution of things. So just waiting and collecting more data helps you. But underneath the last 20 years, we've also had tremendous progress in our ability to obtain these images. So for the first 10 years, we used a technique that's rather simple. I like to call it poor man's adaptive optics. It's simple, straightforward, but it gets you started. So we always knew that there was the more powerful technique coming along, but effectively we weren't willing to wait. So when I first started, there was an instrument at Keck Observatory that was designed to take images, what we call direct images, so not correcting for the Earth's atmosphere. So all we had to do was change the plate scale, the optics out front, so that you could see your scale was much, much smaller. And then to change the electronics so that you could read out pictures fast enough to keep up with the atmospheric changes that are happening, basically mostly in the jet stream. So these were fairly straightforward changes to make, and allowed us to get the first decade of work, get going in first decade. And on the left, we're seeing this bug splat pattern, the speckle animation. So these are just the straightforward data that we collected. So it was hardware simple. In other words, these changes cost on order of tens of Ks. It wasn't a really a huge investment from a technological point of view. And then the hard work at this phase was about the reconstruction. How do you actually correct, pull out what's the object versus what is atmospherically going on. In the beginning, we actually did something very simple. In fact, that's always been our approach, which is you do the simplest thing that gets you to the answer. So on the left, you're seeing the 1/10 of a second exposures. Now on the right, what I'm showing you is what we could achieve in the center. Of course, we're doing this over a much larger field of view, and you can see what's going on. And I have to say, I love showing this image. I mean, it looks, it's not a gorgeous image in terms of the images that we can show, but I have to say I have a particular love of this image. This is really the data. There's nothing cleaned up about it. It's there's no deconvolution that's gone on. There's just simply the I mean, there's some deconvolution to get to the diffraction limit, but we haven't cleaned it up beyond what you would do scientifically. And the reason I like to show this, especially if there are students in the audience, is that when we first started this experiment and put the first proposal into the time allocation committee, it was actually turned down because people didn't believe that these techniques would work at Keck because it was a segmented mirror. So you really have to have the mirror phased perfectly in order for these techniques to work. And then there was also skepticism about whether or not we would there would be stars in this region, or whether or not you could even see the motions. And so that tells you why I like watching this, because it doesn't take a computer to tell you that there's something interesting going on. I mean, A, the technique worked, B, you see stars, and they're just hauling. You can probably identify my favorite star in the universe, and the one that really has the scientific power to tell you what's going on at the center of the galaxy. But already we knew we were well on the way. We also understood that at this point, I mean, this is actually fairly far into the experiment, that we were going to get far further than just simple velocity measurements, and that full orbits were coming along the way. Since then, and what we understood was coming along, was the technique of adaptive optics. Adaptive optics has a really interesting story, in the sense that, of course, there are multiple communities that are interested in seeing through the atmosphere, both up and down. Of course, the military being the community that has far more resources than the astrophysical community. And so there were these two communities that were developing these techniques for high resolution imaging through this technique called adaptive optics. And it was declassified in the early 90s, once it was recognized that the astronomers were really making a tremendous amount of progress. So in the early 90s, there was a real leap forward in terms of making progress in getting these techniques to work on large ground-based telescopes. This just conceptually shows you what's going on. It shows you the light path of the photons coming into the telescope. So it bounces off the primary mirror, goes off a secondary, and then comes into a port where often instruments are kept. At Keck, this is actually not where the ones that we're using are located, but this just conceptually shows you what's going on. So we're going to look at the interior working of the adaptive optics system. And so the light comes in, and the second bounce here is off of a deformable mirror, and that's really where the power happens. So this optical element does exactly what its name suggests, but it deforms. And so the goal here is for the mirror to take on the shape, to be conjugate, to be conjugate to what the atmosphere is imposing on you. So here we have wavefronts now. The atmosphere has imposed some distortions in the wavefront, and what you want to do is have the deformable mirror take on the opposite shape, so that after it reflects off the surface, in principle, it becomes completely flat. And ideally, one then gets a still image. Today, with today's technology at the Galactic Center, we correct for roughly 30%, but that's actually good enough. You get a diffraction limited core that has 30% of the energy. And that's far better than what we were doing with Speckle, which really only had 3% of the energy, which, if you remember Hubble Space Telescope before it got its optics fixed, that was effectively the same kind of image quality that was happening then. Okay, so this has been tremendously powerful, and the key to really making this scientifically productive is the ability to use lasers to create the reference source that one needs in order to tell the deformable mirror what shape to take. So these lasers are taking advantage of a fluke of nature, in that in the atmosphere, it turns out that there's a layer of the atmosphere up at 90 kilometers that traps sodium atoms that are deposited by meteorites. So again, just a fluke of nature that we have meteorites that are depositing sodium atoms, and they get concentrated at this very, very high altitude in a thin layer, so that we can shine a laser tuned to a transition in the sodium atom and create an artificial star that's very bright, no matter where you look. So this is a picture I particularly like. It's a night that we actually had time on both telescopes. Both telescopes have adaptive optic system working, and we were able to point the telescope, both telescopes, to the center of the galaxy. So it's like having two giant laser pointers telling you where to look to find the center of the galaxy. The fact that you can see the yellow light is actually just that the light's scattering off of dust. It's actually not, all the power is actually happening at the end where it's generating this artificial star. Okay, now with adaptive optics, you can image much, the image quality becomes much better in almost any way you can characterize it by about a factor of 10. So this is the exact same field that we're looking at. And again, this is the very small region where you think the center of the galaxy is, or where you think the black hole is. So you can see the stars that become very important. But in addition to being able to take images, and before we could only take an image at a single wavelength, now we can take images at multiple wavelengths because we can take longer exposures now. And for the first time, we can get spectra. And this is incredibly important. So it's much harder work because spectra, of course, require you to expose for much longer. And the fields of view become much smaller, just simply because the detector real estate then goes into wavelength coverage, not just plane of the sky coverage. So these are instruments that are called integral field units that give you both spatial and spectral coverage. So from a physics perspective, in terms of this experiment where we're after the orbits, the spectra is important because the images just give you the motion on the plane of the sky, and that gives you a lot, but you're missing the motion along the line of sight. So you're missing that third dimension of motion. So your ability to get spectra allows you to solve that missing dimension. And then from an astrophysical point of view, for the first time, you get to understand these sources as more than point particles that we like to talk about in freshman physics. And we get to ask what the astrophysical nature of these sources are. And there's been an incredible number of surprises. I'll just briefly say, this is showing you two spectra of stars. The population divides very strongly into just what I'm going to call an old star, which is a star that's roughly 1 billion years old. And you see very strong features. And in particular, you get sodium features. So the atmosphere is much cooler, so you get different transitions. And then the young stars, which actually have atmospheres that are much hotter, you get a transition in the hydrogen atom that is found in the region that we examine. Okay, so this will become relevant. I'll come back to this. Oh, right. So I just wanted to note that, this experiment has been so interesting in terms of the evolution on so many different fronts, both in terms of the technology, the science, but also just the way we take the data. When we first started working, we went to the summit, and that's what you see on the top left. This was the second year that we got data. And I think this is a picture when we realized how well this is going to work. Either that, it was the altitude that made us so happy, but this was really an interest and a wonderful moment where we really understood how much better this was working than we had ever anticipated. But we were up at 14,000 feet. And if you've ever hiked or worked up at 14,000 feet, presumably you also know that there's some interesting challenges associated with thinking well. Then it became possible to observe from the headquarters. So in fact, the vision of this telescope was always to be able to observe from Waimea, which is where the headquarters are. And of course, there are lots of benefits to coming down from the mountains, and there's a lot we miss. Up at, when we went to Mauna Kea, it was wonderful in terms of having telescopes from all over the world. This is much, you were just mentioning at the beginning of the talk, the canteen, the conversations over coffee. So what I miss is breakfast or dinner with scientists from all over the world up at Mauna Kea. And that's the thing I think we really miss tremendously, is that scientific interaction. Everyone's now in their own little telescope or observatory bubble. So we came down to Waimea. Then roughly 10 years ago, it became possible to observe from East Campus. And of course, CERN is very familiar with remote operations. And then because of COVID, the telescope for the first time enabled us to work from home, something that the observatory had been really, really quite resistant to. But I'm really grateful for the willingness of the observatory to open up that capacity. So, you know, we zoomed to the telescope or tunneled in. Okay, so this is today how SO2 has moved over the last 25 years. This animation now is a quarter of the real estate of what I was showing you before. And the information that's contained in this image is that when you're detected in an image, the star is trailed by a dashed line. So there are some stars that appear halfway through the animation, and that simply reflects that your imaging techniques or technology has changed so that you can see objects that are much fainter than in the beginning. And then when you're the star is trailed by a solid line is when that star has been successfully measured spectroscopically. So there's been an evolution, not only in the adaptive optics, but the instrumentation behind the AO system that has gone from only being able to detect SO2 to a much larger population of stars. But you can see why SO2 becomes so important, because it's the only object that has gone through a full orbit, both astrometrically from an imaging or positional point of view and spectroscopically in terms of the plane of the sky. So it's the one that gives us the most power in terms of understanding the central potential. So to show you data, real data as opposed to animations, this is on the left, basically the position information, so X, Y, on the plane of the sky. And this dashed line shows you the intersection of the orbit with the plane of the sky, so how things are oriented front back. And then the radial velocity, which is the motion or the speed along the line of sight, is shown here on the right. And it's just simply remarkable. I mean, you can also see this first measurement, in fact, was so noisy we couldn't pull it out in the beginning, but it was only after we had knowledge of what to look for. In other words, the ability to use priors, that we could pull out this initial point. But the changes are remarkable. You're going from 4,000 to minus 2,000 kilometers per second in the space of a few months. So at this point, when this was happening, we didn't know the full the orbital scale yet, and it was only after this first closest approach that we realized we had a short period star. So we had an orbit of 16 years. So that both gave us the ability to really measure, not just from a velocity dispersion. So I've skipped over many steps of this experiment where we've gone from velocity dispersion to accelerations. And each step is a tremendous advance in terms of your ability to constrain what's at the center of the galaxy. But let's just compare our knowledge before we started this work, where we knew there was 4 million times the mass of the sun inside this region that's demarked by the line. And at this scale, you're so far away from the short shield radius that no one is, actually at this point, this is actually some of Charlie Towns's beautiful work. There's a small mention in the paper that it might be, but that I think really reflects that there were so many alternatives that it was difficult to make the case. And with the orbits now, we've confined the mass to a region that's 10 million times smaller. In other words, the implied dark matter density has gone up by a factor of 10 million over the course of this work. So we've now shown that, in fact, there's 4 million times the mass of the sun inside a region that corresponds to the scale of our solar system. And that is what has provided us with the strongest evidence for a supermassive black hole. So if you want to look at this in terms of how we've made progress in terms of the mass of the dark object and the dark matter density, which is how people often argue the case, the green line here shows the lifetime of clusters of objects going from timescales that are longer than the age of the universe to shorter. So in other words, the goal is to get well above this line to rule out the possibility of dark clusters of dark objects. So these red arrows go from the beginning of the experiment, which is where that big circle was, to velocities, and then all the way up to orbits. So we've increased the case for a supermassive black hole by a factor of 10 million. I should also point out that along the way, as the case was becoming stronger, there was a really fun suggestion that came out of the particle physics community, which is the idea of a fermion ball. So this is the equivalent of a neutron star, but rather than being made of neutrons, it's made of fermions. So it's a compact object that is uniform density, but its scale is much, much smaller. So it was only by the time that we achieved orbits that one can actually rule out the fermion ball hypothesis. Okay, so this is the work that's being recognized by the Nobel Prize. This is actually a picture that was taken from the Crawford Prize 8 years ago, but I wanted to put it up here to recognize that there have been two groups that have been pursuing this project for the last 2 decades. And it's been tremendously helpful, in my opinion, to have two groups that are going after this from independent points of view, different telescopes, different technologies, and also different analysis methods. I mean, as this community is very familiar with, oftentimes when you get into precision measurements, it's all about your data analysis in terms of really understanding your statistical uncertainties to get to the ultimate results. And this is going to become more important as we go along here. Okay, so I just want to share now that we have the evidence for a supermassive black hole, the interest in my mind now turns to no longer proving that there's a supermassive black hole, but rather understanding the physics associated with supermassive black holes. So there are two completely different directions, each of which have many branches, but I just wanted to give you a sense of where this project is today. So on the one hand, we want to understand the astrophysical role of these black holes with respect to the formation and evolution of galaxies. And it's also interesting to note or to recall that even our thinking about that question has evolved tremendously over the last 20 years. When we were first coming out with these, the velocity dispersion results, which was the late 90s, the question was phrased as which came first, the galaxy or the black hole, sort of like the chicken or the egg question. And we had lots of theories to explain as a community how you could either see the galaxy with the presence of a supermassive black hole, or how you could form a galaxy and through collisions form the central supermassive black hole. But in fact, over the last 20 years, the thinking on this has changed dramatically, because as there's increasing evidence for supermassive black holes in other galaxies, as we look at the relationship between the mass of these black holes, these supermassive black holes, and the mass of the central component of these galaxies known as the bulge, there's a very clear correlation. So the black hole seems to be roughly 0.1% of the mass of the central bulge. And the scale of the bulge is so much larger than the scale of the black hole that leads to the presumption that whatever formed the galaxy had to form the black hole as together synergistically, that it's not one then the other, it's not causal, it's synergistic, and that there's some feedback between the black hole and the host galaxy to maintain that relationship over time. So now that we think of it this way, we have the opportunity at the center of the galaxy to look for evidence or of that feedback mechanism. And what's so interesting, in particular as adaptive optics has come online, is that almost every single prediction that one can make about the stellar population that you should see at the center of the galaxy is inconsistent with the observations. So to me, this is, I don't know, call it job security or just the pleasure of being a scientist, and really the wonders of working with new technology, because it gives you a viewpoint that you simply didn't have before. So sorry, this for some reason this isn't playing smoothly. This animation is designed to play smoothly, and it's pulling back. It's our knowledge of the orbit so far pulling back. And here you can see some important pieces, which is at some scale, both in terms of distance to the black hole and viewing angle, you see there's a co-alignment of objects. So this has become important in terms of understanding some of the interesting paradoxes that have emerged. So to just briefly give you a sense of the interest that's emerging here, there are two predictions that I'm going to briefly describe. One is that near a black hole, one should not expect to see young stars. Young stars form out of very fragile clouds of gas and dust. And in order for star formation to proceed, you need those clouds to collapse under their own self-gravity. But if you put that cloud near a supermassive black hole, the tidal forces can easily overcome that self-gravity and will lead to these objects being torn apart. So especially if you look at the densities of the densities are simply orders of magnitude, and I mean like 10 to the 11 off from what you need for self-gravity to overcome the tidal forces in this region. So in fact, in the 80s, it was argued that young stars in this vicinity, in fact, outside, roughly at the edge of this animation, which you could see with direct imaging, the presence of young stars was argued as a reason that our galaxy didn't harbor a supermassive black hole. So now we have a really interesting problem, because in this animation, the young stars are the aqua objects, so the blue-green objects. And in fact, that's the most prevalent thing we see. The thing that we actually predict shouldn't exist or is in contradiction or opposition to the idea that there's a supermassive black hole. So this is a fascinating problem, which I like to call the paradox of youth. These objects are only a few million years old. They're definitely early, very young stars. And this has driven theoretical development in a number of different directions to explain the presence of these apparently young stars. So you can either argue that they were formed far away and migrated in very quickly. To do that, you need to invoke intermediate mass black holes as the delivery mechanism, because otherwise they don't migrate in fast enough. You can say they're actually old stars that have somehow been altered by this environment. And that's not an unreasonable assumption, but to the fullest extent that we can tell, these really do look like typical young stars. And then the third idea is that the environment was very different at the time of their formation. And that's the explanation that the commonality of the orbital plane points you to, because then because an orbital plane suggests that there used to be an accretion disk, suggests that had much higher gas densities that could lead to the formation of these young stars. The corollary to that idea is that at the time that these stars were being formed, our galaxy might have been a much more active galaxy, very much like those active galactic nuclei that made us think of supermassive black holes in the first place. So it's interesting to think about how different our galaxy could have been, and what drives the growth of both the galaxy, the stars, as well as the black hole itself. So that accretion material, all the gas, actually could have been an important input to the black hole, whereas the disk itself also is forming the mass that goes into the stars. Okay, so that's problem number one. Problem number two is that you expect that interactions over 1 billion years should lead to what's called a cusp, or an enhancement of the density distribution of stars near the black hole. So you should see lots of old stars. The orange things in this animation are the old stars. So in fact, you see the opposite. You see a dearth of the old stars. So there's a question of, where did the old stars go? I don't have a good explanation yet. I have a lot of ideas, but no good explanation. And then the third thing that's really entertaining that's been discovered where there was no predictions are these magenta things. And these magenta things are objects where you actually see the tidal interactions with the central black hole. So as they come through closest approach, you can actually see spatially resolved the outer layers being torn off the object itself. So there was a tremendous amount of debate over what kind of objects these are when they were discovered just 8 or so years ago. But there's no doubt that there are these tidal interactions, and these tidal interactions are probably an important mechanism for feeding the central black hole. So initially there was a lot of suggestions suggesting that maybe these were just gas clouds, but these things have survived their closest approach, which tells you they have to be stars. If they're central stars, they have to be 100 times bigger than anything that we've talked about existing at the center of the galaxy. So then the question becomes, how do you get objects that are 100 times bigger than you would expect? Oh, I'm thinking, okay. This is supposed to be an animation. Unfortunately, it's actually not playing. It's showing you that one of the anticipations of all of this is that the black hole should accrete and respond to matter being dropped on it. So this is actually real data that shows the color of both Sagittarius star, so an object. Oh, Sagittarius star is the emissive source associated with the black hole. It has a very different color than the other stars. And you can see this. This is just the combination of 3 images at 3 different wavelengths, 1, 2, and 3 microns. So one of the things that we've had, that we've invested a significant amount of time that you might find somewhat entertaining is that one wants to understand how to understand if the black hole is reacting to something that's flown by it. And the black hole's changing in brightness all the time. So you want to make sure that the next time it goes blip, you don't get excited about maybe a closest approach. And so we actually collaborated with somebody in the business school who is very familiar with variable markets. So we've applied these techniques used in finance to describe whether or not there's an emerging second, what do I want to say? That the light curve has assumed a second characteristic, so statistical property. So of course, the financial world cares tremendously about that. And that's allowed us to actually say whether or not the black hole is responding to these objects. Now, my favorite current hypothesis for these tidally interacting objects is that the black hole may have driven binary stars, pairs of stars to merge. So it's just a 3-body interaction. So most stars actually form their life as binary stars. This is something that we know from our solar neighborhood. And but of course, as we always do, we always assume the simplest model. So people weren't really thinking about what would happen if you put a binary star near a supermassive black hole, but it just becomes a 3-body interaction. And there's something that's known as the Kozai-Lidov effect, which is effectively where the close binary exchanges angular momentum with the orbit around the supermassive black hole. And that exchange of angular momentum can drive these 2 stars to very high eccentricities. And at the highest point, when they, in principle, can merge. And if they merge, they become like, it's resetting the clock, and they become very inflated for roughly 100,000 years. So that very naturally produces objects that are big enough to explain this tidal interaction. Now, the reason I find this so fascinating is not just because you explain these tidal interactions, but because it may provide a connection or an understanding to the sources that are being detected by the gravitational wave detectors. So LIGO and Virgo are detecting stellar mass black holes that are much more massive than they expected, and the mergers are happening more frequently. So one possible mechanism is that we have stellar mass black holes interacting with central supermassive black holes, and the mergers, the succession of mergers can drive stellar mass black holes, which are anticipated to be roughly 10 times the mass of the sun, up to the 30 times the mass of the sun. And because there's a driving mechanism, it can also create these mergers rates that are happening at a higher rate. So this is now something that's being thought about in the gravitational wave community. So it's interesting how unexpected observations with these different techniques can actually help to inform each other. So now one of the things that we're very focused on is actually looking for the presence of binary stars at the center of the galaxy to really understand at a deeper level these possible connections. Now, I'd like to end with just a few words about gravitational physics, because this is an area I find particularly exciting at the moment. So SO2, having gone around once, the anticipation has been actually for quite a long time now that one can start to test the effects of general relativity, theories of general relativity with the orbit of SO2. And there are two tests that are actually both within reach. One is the relativistic redshift, which is just looking at the photon trip from the star to our telescope, and then the precession of the periapse, which is just looking at the how the object moves through space-time. So I'll just quickly say that the relativistic redshift is most easily seen at closest approach, but you need to understand the shape of the orbit. So basically you need the whole orbit to get the seat at the table to make these measurements. And in 2018, so we were 2018 or bust for this measurement. And it was just remarkably fun, and I can say more about this if people are interested, to see this emerge. So on the right-hand side, actually, let me just explain. On the left, we see the Newtonian piece. This is the 4,000 to minus 2,000. On the bottom here is the anticipated model for what GR tells you, that there should be an extra 200 kilometers per second at closest approach. So your biggest problem is actually knowing the shape of the orbit to see this extra piece. And it beautifully matches. So this is the extra piece above the Keplerian velocity along our line of sight. So this is the loss of energy that the photon experiences as it climbs out of the central potential at closest approach. Now, the next thing is the precession of the periapse. And what general relativity tells you is that the object should not come back to the same place, but there should be prograde motion. So you get this spirograph pattern. This is an exaggerated view of it in terms of that orange dotted line, but you expect prograde motion. And the signal should emerge, you expect, after this closest approach as you head towards the next furthest approach. But what's interesting about our data is that the orbits actually are precessing in the opposite direction. So instead of being prograde, they appear to be retrograde. And so this is causing us to scratch our heads a bit. And what can cause retrograde motion is the presence of dark matter, be it in the form of particle physics, particles, or stellar remnants. So it's still early days, but I'd have to say this is the thing that I find most intriguing about the current experiment. To make progress, of course, we can just wait, but we can also improve our technology. So today we're developing a new adaptive optics system in collaboration with Keck Observatory, and in particular, Peter Wazinowicz, where we launch multiple lasers so that we can basically make a tomographic map and increase the amount of wavefront error that's corrected. And all of this is absolutely critical if you want to get to the next level of telescopes. And of course, there are 3 telescopes around the world that are in progress: the European Extremely Large Telescope, the Giant Magellan Telescope, and the 30-meter telescope, which is the one I'm involved in. But the larger your telescope, the less effective a single laser is. So this advance in adaptive optics is important, not only for increasing the scientific potential of the existing telescopes, but mitigating the technical risks for this next generation of telescope. Okay, I'm just going to end by saying there are lots of students involved. Actually, let's not skip that, because I want to give great credit to Mark Morris and Eric Beckland, my long-term collaborators, and then Jessica Liu and Tuan Do, who were originally students and then have become my long-term collaborators and have been played really critical roles in the success of this project. So if nothing else, I hope I've convinced you that our galaxy harbors a supermassive black hole. And we even proved the case with this experiment by a factor of 4 supermassive black holes by a factor of 10 million. And this has provided us with a wonderful laboratory for understanding both the fundamental physics of black holes as well as the role that black holes play in the formation and evolution of galaxies. Thank you for your attention.
Thank you, Andrea, so much for this fantastic talk. I'm sure there are many questions. Please raise hands or type in chat if you don't want to speak. Are there questions? Okay, Alexas.
Hello. Thanks for a fantastic talk. I wanted to ask, are there any stars which would be on a trajectory to go particularly close to the supermassive black hole? For example, in this figure, at the moment, I see one incoming star which seems to come very close, but I don't see if it's already followed up, or is it just an illusion that it comes close?
That one, it actually does come quite close, and why the reason it's not more powerful is that you don't have the complete orbit. So it's dominated by uncertainties in the shape of the orbit. So you need a star that comes close, but that has a short enough orbital period. So there are other objects that are here. In fact, I'm realizing this particular animation doesn't show all of the shorter period stars. Some of the shorter period stars we only see in images. So part of our real drive to get to this next generation of adaptive optics is such that we can make the spectroscopic measurements that go along with the images and really have those stars partake in these experiments. Okay, I think. Let me just say one more thing, because another thing that may not be obvious, it's often, I mean, it's hard to give enough detail with all of these topics. One of the things that one has to worry about most in this precession project is your understanding of your astrometric reference frame. So in other words, you need to put all your measurements into a common coordinate system. Spectroscopically, there are well-trod ways of doing this using transitions in atmospheric lines that tell you what the reference frame is. But the imaging reference frame is much harder to establish. So you have to ensure that any rotation in either direction isn't caused by your reference frame. So that if you want to ask about like what makes that measurement hard, it's that piece. So in fact, the other stars can play a role in just controlling your knowledge of the reference frame, even if they're not getting at the physical process. They're playing an important role because they help you set the reference frame.
Okay, I say thank you for Alexas, and next one is Ruth.
Yeah, my question was similar, namely in units of Schwarzschild radii, what are the closest stars? How many Schwarzschild radii away are they from the central black hole?
Yeah, they're about 500.
Mm-hmm. Thank you.
Yeah.
Next one in line is. Yeah.
So actually, just to give you context for that, so you're closer than the binary pulsar case, but you're still far out. So if you want to be skeptical about the black hole case, you're still, there's still wiggle room.
Okay, so next one is Luca Giangrande. And well, I'm supposed to read it. The question is, do you expect any particular gravitational interaction between supermassive black hole and dark matter?
Oh, that's an interesting question. I don't know, but you might. And you also might ask about the interaction with the stars themselves. So another thing that's been explored is it possible to explain the young appearance of these stars by thinking about dark matter infused objects? So there's definitely ample questions that I think we're only beginning to ask about.
Okay, next one was W.A. Horowitz.
Thank you so much, and thank you very much for a really, really great talk. I apologize if you get this question a lot, but would you mind speaking for a few words in terms of reaching the absolute pinnacle of science as a woman in your career trajectory, and then also how we may more effectively attract and then support women in the sciences at that kind of level? Thank you.
It's actually a harder question. That's actually harder than the science questions in terms of answering. So, I've just pursued my science because I love it. I think I've been very fortunate to be in places where I've worked with wonderful people, and I think that's critical to understand as one goes along, where I think this is generally true, but I think maybe women face a few extra hurdles in terms of understanding who's going to support their careers. So having advisors who really have their back. One of the things I've realized in retrospect, so while I was coming up, there certainly were very few senior women. So I realize in retrospect that I think all my mentors had daughters my age. So I think that's a piece of advice I used to give to people, just to understand, your mentor's true belief in you, because, as we all know, those people have incredible impact on how you go forward. I mean, not only in terms of how they teach you, but also the doors that they open. So I think I was very fortunate and made a real effort to really understand where I would have opportunity. I would also say I probably understood. I was an undergrad at MIT and a grad student at Caltech, and I think when I decided to go to Caltech, I think I understood that it was worth going to a place where people would take me very seriously. In other words. To give yourself the most, used to say I think often as a woman, you're assumed stupid until you prove you're smart. So what can you do to ensure that people take you seriously? So I think I was very conscious of that. And I think I was very conscious of the fact that there weren't a lot of role models. So I really appreciated the ones that I had in my life. So today, to answer the second part of your question, I'm not sure I've done a great job with your first question, because of course it's really hard to have self-reflection. The other piece, I have been very interested in the concept of the importance of strong visible role models, which is why when I teach, I always teach at the undergrad level, at the very introductory level, because I think if I have to teach, that's where I can have the biggest impact, just by getting up and showing that, who looks like a scientist. There's a variety of people who do science, and just to bring the enthusiasm for research into the classroom. So, and to be willing to do, talks and engagement, and to go to different universities and engage with the students about science. I mean, really to just talk to them about science. So I guess that's my answer. So I'm delighted to be awarded this award in a way that gives successful women more visibility, because I think just understanding that there are women out there who succeed, it has a huge impact.
Well, judging from the enthusiasm you emanate here to the dry particle physicists, and indeed I think you really do a good work here. So next one is by Adam Jacholkowski, and he's asking, what is the expected far future of the supermassive black hole?
Oh, they're the ultimate survivors. So if you think about the ultimate evolution of the universe, it's a very dark place, but it is the black holes that survive the longest. So I guess I would say ultimate survivors.
So a dull future, actually.
Yes, it's dull.
So next one is Ashutosh.
Actually, to go back, there is a great book on this. So Fred Adams wrote a book called The Dark Ages, where he evolves the universe out to its absurdly long evolution. So if you're interested in that question, I recommend that book.
Yeah, I think it's very depressive, this future. Thermal equilibrium. So Ashutosh is the next one.
Thank you. Thank you for that beautiful explanation of how your techniques developed and how beautifully they worked here. My question is, what are the next steps in accumulating more information about supermassive black holes at the centers of other galaxies? How far would these techniques that you described here keep working? And at which point would you need, the galaxy becomes too far away or something, and other techniques would be needed to collect more data on more supermassive black holes? How do we evolve from here?
I think, I mean, we're in a moment of tremendous potential for further research on supermassive black holes. I mean, as we get to larger telescopes, you can just expand this to the nearest galaxies. But we're also at a point where we're talking about expanding the gravitational wave experiment from LIGO to LISA. So LISA, which is the space-based facility, will open the ability of gravitational waves to probe supermassive black hole mergers. So I think that'll be an important development. Another experiment that I think is really interesting in terms of helping us understand supermassive black holes is the Event Horizon Telescope, where we've already seen the results from M87. So this is the worldwide telescope where they combine light that's taken at radio wavelength. So it's important to recognize that each one of these facilities is really probing a very different window. So the kind of work that I'm talking here, you're looking at infrared wavelengths that probes the stellar response to the response of stars to the gravitational potential, and gravitational waves, of course, are just gravitational waves. And the kinds of GR tests that you can probe are different. So I think that's exciting. With the Event Horizon Telescope, you're looking at radio wavelengths. So you're really looking at emission from gas. And what they're looking at is emission that's from behind the black hole, and the black hole is gravitationally affecting the trajectory of the photons, the light. So you're looking at the presumably what corresponds to the photon ring. The two cases that experiment can do is M87 and in principle our galaxy. So I think a lot of people find it very surprising that M87 was easier than our galaxy to image, and the reason for that is M87's black hole is larger. So the dynamical timescales outside the event horizon are longer. So for the Event Horizon Telescope to work, you need the object to be static on the timescale of the Earth's rotation. So our galaxy, the black hole is less massive. So the timescale for variation of this light is changing much more rapidly. So it's a much harder imaging problem because the structure of the object itself is changing on timescales that are shorter than the timescale for the revolution of the Earth's rotation. Nonetheless, it's just an imaging problem. So it just means you have to be more clever, and it takes more work. But I suspect we'll be hearing more from that project.
Got it. Thank you so much again.
Mm-hmm.
Okay, next one is a daughter of Richard, who is asking if by modeling the stars' collective motions, whether you can say anything about the motion of the black hole itself.
So I mean, that's an interesting question. So in principle, you can. This really gets back to this question of the understanding the reference frame that you're in. So without going into too much detail, we try to get into a reference frame which we call a Sagittarius star rest frame. In other words, by definition, we're in the reference frame where the black hole is at rest. You can think about other reference frames, or think about trying to understand the possible binarity of the black hole. In other words, is the supermassive black hole orbiting another massive black hole in its vicinity? So these are things you can currently constrain and might be of interest.
Richard and his daughter, thank you for the extremely inspiring talk. Next one is a friend of Federico.
I can ask myself, Wolfgang.
Oh yeah, okay, please go on.
Thank you very much for the beautiful talk, and congratulations, of course. What I was wondering is that if there is any way that if this idea of mergers is correct, that somehow this can result in the appearance of apparently younger stars, I don't know, shedding the heavier nuclei or something like that. I'm asking for a friend. Yes.
Oh yeah, I'm very intrigued by. So one of the things I've sort of simplified the young star story. So it turns out that there are two populations of young stars that look different from one another. So the stars that are actually inside this box that we're looking at here, the young stars that are in this box have a slightly different characteristic to the stars that are in the plane, and the plane only develops at larger radii. So one of the things that I'm quite interested in understanding is whether or not stars like SO2 are the evolved product of a binary star merger. So, you know, there are other contexts in which we know we see binary star mergers, such as in globular clusters. They're called blue stragglers, simply because there's a clump of stars that have characteristics that are a little different. And today we understand them as binary stars that merge. So I think that's a really interesting thing to consider, and something we are thinking quite a lot about. I don't think at larger radii the younger star population that forms a disk can be explained by this mechanism, though.
Thank you.
Okay, next one is another stand-in question. Victor, the 10-year-old son of Rodney, is asking how long in Earth years does it take for a star such as SO2 to go a full orbit around the supermassive black hole, and how long would it take if one would be sitting on this planet, on the star itself?
So it goes around every 16 years. And to the extent that we can measure it, everybody's going to agree from here or there about that time scale. Let's see what else interesting thing. I mean, 16 years, I have to say, it's so profound to me that we can see something go around the center of the galaxy on a human time scale. And maybe to put this in context for the person who asked this, you know, the sun takes 200 million years to go around the center of the galaxy, and so you wouldn't possibly consider making such measurements, and that's part of why in the beginning we were only thinking we were going to measure little arcs, because we didn't understand that these stars were going to be so close.
Okay, so
I'd like the bigger telescope, because the time scales will be shorter, and I'm getting older, so not so patient.
there was a second part of the question, but I can answer it right away, namely whether there's a sizable time dilatation, and for an orbit of 16 years, there's essentially, so it would feel like 16 years, I guess.
Yeah.
So next question, I think, is by David Lunny.
Yeah, hi. Andrea, thank you very much for this great talk, and congratulations for your well-deserved prize. I'm working at CERN on an antimatter experiment where we're actually testing also general relativity, but we want to stop antimatter and drop it, see if it drops at the same rate. If you ever visit CERN, we'd love for you to come by to visit us. It's on the way to Stockholm. On the way to Stockholm, so.
Okay, next year.
Yeah, so there are 3 experiments doing that. So there's competition, and I wanted to ask you about. You shared the Nobel Prize, and you mentioned the important fact of having, let's say, competition. Could you tell us how they complimented you, or if they tried to scoop you, and did you have real competition with them?
God.
Sorry,
I wish I'd kept the diary. Oh yeah, no, it's okay. It's an important question actually. It's important I'm so grateful that the Nobel Prize was willing to recognize both teams, because I think competition is so important on so many different levels. I truly wish I'd kept a diary through this whole process, because 25 years of, having this evolving relationship with a different group. It's an interesting thing to grow up scientifically with. I mean, if you think about this, like I started my faculty position doing this work in competition with this group. So it's been 25 years of this head-to-head. Wow. I think it's interesting. It keeps you on your toes. I guess I've been a big believer of keeping the 2 groups independent. And I think the science has really benefited from that independence of thought. I think I've learned all sorts of interesting things that are on a more sort of how to become, it's like you have to think about what kind of scientist you want to become, and how you deal with competition, how you talk about competition, how you talk about agreements versus not agreement. So I'm really grateful for this. It's like it's part of how we do science, right? So much of science is sort of this critique of everybody's work, and it's so easy in this project actually to hide the details. I mean, you can kind of see in this talk, I haven't told you anything about what's really hard about it. It all looks really easy in retrospect, but there are things that made this hard. There are things that the 2 groups have not agreed about over the years. And so it's really interesting when the 2 groups don't agree, because then you have to scratch your head and ask, well, why? How is it that we're getting different answers? And you would know, and it just means that some of the analysis is difficult. So here's an example of one. The idea that stars at larger radii share a common orbital plane. You're not measuring the full orbit for those guys. I mean, it's a simpler problem, because you're not trying to get all the orbital elements, because you use SO2s to constrain the central potential. So then you're just looking for the stellar orbit. But those orbits are 400 years long. So you have a probability distribution function that's pretty big, and you have lots of stars. So how do you correctly combine your partial knowledge for a big set of stars? There's been a lot of controversy around how to do that right, how many disk planes are there, and it just forces you to think more carefully when the answers are different, and so so we share in the way that science we do share, like through publication, but we also do it through talks, and I think this is something that's interesting. Like in effect, the idea of which way things are processing, the 2 groups don't agree right now. And so it's interesting, how do you talk about this? So what am I doing right now? I'm basically informing everyone, I don't agree. I'm not publishing it because I'm not ready. I don't believe it yet. In other words, and that's been a characteristic, I think, of our group. We've been more conservative with. I mean, it's a philosophical approach of, you know, when do you publish? So, and maybe that's important too, which is the two groups have had incredibly different styles. And maybe that's good for science and good for the next generation to just see that there are different styles and that you benefit. I mean, I think we've benefited tremendously from the existence on so many different ways. I mean, some of this is certainly hard to talk about. It's certainly hard to talk about publicly. But I think ultimately the science in many different ways has benefited from the existence of the two groups, and the two groups maintaining a fair amount of independence. And of course, it's not complete independence because we're always publishing. So, you know, you keep learning to the extent that you've actually put in your papers enough information for the other group to figure it out. So that's also an interesting, just again, an interesting part of the sociology of science. Like, what do you share in your papers?
Mm-hmm. Yeah, totally agree. Have you consulted, let's say, some experts on general relativity about this precession, whether it could be explained by something different about gravity?
Yeah, we're not, I mean, I think right now I'm too worried. Actually, what I'm really worried is about this reference frame. I mean, if you told me 20 years ago that the thing I'd be, you know, waking up and thinking about is the reference frame, I would have thought, oh my God, my life is going to get really boring because it's a really dull topic. But of course, if it's the thing that limits you to getting your science, it becomes the thing you're most fascinated with. Like, how can you go wrong? How can you make it better? And you know, and this also gets into the confirmation bias problem of science. Like, why are you so worried? You have an idea about what the answer should be, which is also, I think, one of the fundamental challenges with these fundamental tests of how do you make sure that you don't just get what you think the answer should be.
Thanks a lot for the discussion.
Thanks for the question.
All right, next question is by John Meshrecki, and he asks, could you please quickly talk about how much do we currently understand regarding the physics inside the supermassive black hole, and what are the challenges?
Very little. You got to ask Penrose these questions. So from an observational point of view, you know, we're left with the problem that we can't get information from inside the Schwarzschild radius or the event horizon. And I think that's a really interesting challenge in terms of how do you push forward from an experimental point of view. So there are a lot of theoretical ideas, but how do we confirm or how do we make progress? And I think, you know, the current thinking right now is that one looks for or hopes to find the imprint of the physics that's presumed inside, outside. But, you know, one of the interesting things about black holes, and I think what that makes black holes so fundamentally interesting, is that their existence in some sense is pointing out the limitations of our understanding of gravitational physics. You know, so that's a mushy answer, I realize, but I don't have a good one.
Okay, thank you. I think nobody has a better answer anyway. So next question is by Vladimir Lenok. Some measurements show that the dark matter is distributed like a cloud around some galaxies. Can you say that what we observe in the center of our galaxy is essentially the gravitational physics without the dark matter influence?
Let's see. So what was the first part, the dark that we see?
Maybe I was misreading it. Can you say what we observe in the center of our galaxy is essentially the gravitational physics without dark matter influence? So
I can comment on my question.
Okay, good.
I know that from lens measurements and from some other measurements, we can see that the dark matter is distributed like sort of cloud around the galaxy. So there are no in particular clumps inside of the galaxy. So from this perspective, can we say that what we see in the in the center of the galaxy, like these motions of the stars and the gravitational interaction there is, can you say that you see essentially only gravitation and we essentially kind of don't see the influence of dark matter, or you cannot say this?
Okay, so that's what's so interesting about the precession in the retrograde sense. So if this turns out to be correct, that SO2 is precessing in a retrograde, in other words, you're opening up. I realize most people in this audience understand this, but let me explain to those who might not think about this. The simplistic way I like to think about this is that if there's distributed dark matter or distributed matter, I mean, the stars don't care if it's dark or light. You're certainly not seeing a lot of light. The acceleration that one sees at closest approach, you're seeing less mass at closest approach than at furthest approach. So the orbit opens up. So there is a hint that that we might be seeing some additional matter term. I'm not sure I'm getting at your question, but this is to date the best model has been a point, to model it as a point mass. But in fact, we're now and at each year moving toward, this is what's so interesting now is that it just increases from closest approach to furthest approach. At furthest approach, this effect should be strongest, in other words, or most apparent, because just your lever arm is largest. So I don't know yet, I guess is maybe the simplest question. I mean, today we've always said it's just a supermassive black hole. And what's so interesting about what's emerging now is, while what we were going after was the signature, the relativistic signature, which is precession in the prograde direction, so you overshoot. That's not what we're saying. And of course, more stars help you here tremendously. What you really want is more stars that are close enough to be able to detect this. For the extended mass signal, the other thing, actually even for the precession signal, the more eccentric objects are the ones that are most important. So it's very helpful that this is not a circular orbit.
Thank you.
Mm-hmm.
Next one is by Florian Dax, and he writes, I could only join the talk halfway through, so I'm not sure whether this was discussed, but it seems the stars around this supermassive black hole seem to have very different orbital planes. If this is so, and if yes, is expected, or is this expected, or there's something which is still to be explored?
So actually, it's interesting to ask about the inner edge of the. So there is a population that shares an orbital plane. Inside a certain radius, there's no evidence of a common orbital plane, and in fact, that's expected because of the interaction with the black hole. Is that you will ultimately, these orbits will evolve over time, and even if they're young, that's plenty of time for these things for their orientation to move around quite a bit. So yes, you do expect that randomization, and in fact, it's only outside at the point. It's roughly at the location of the inner edge of the disk that you expect things to be able to maintain the signature of any initial commonality. And of course, the older the star is, the larger that distance is going to be.
Thank you. So, next question by Stefano Merzi. I would like to ask a question. Will it be possible to better understand the possible past activity of this supermassive?
In fact, there are different places that you can look that might be connected. So in gamma rays, there's what's known as the Fermi bubble. at very large distances from the galaxy, which suggests past activity. And there's a lot that blows out a bubble, very big bubble from in a direction that's orthogonal to the disk plane. So that suggests that a few million years ago there could have been a lot of activity. The other place that people, or the other evidence for our galaxy being in a much more active state than it is today is by looking at clouds, basically X-ray reflection off of clouds at the center of the galaxy that again suggests in historical accretion rates that are much higher than what we see today. So I'd say yes, there certainly is a possibility of looking for the, that it does look like our galaxy was much more active in the past.
Okay, thank you. Next question is by Barbara Kornvalova. Could centers of galaxies have pairs of supermassive black holes?
Absolutely. And in fact, given that we think that galaxies, one of the primary mechanisms that galaxies grow by is through mergers. And we're certainly, our galaxy's on a collision path with Andromeda, M31. And if we believe that, one of the conclusions that our galaxy, which is completely ordinary garden variety, nothing special about us, has a supermassive black hole. One extension of that is to suggest that most, if not all, galaxies harbor central black holes. So you would imagine that when two galaxies merge, the expectation is that they're going to form a new galaxy. So as we all know, the stars themselves are not going to collide, but you're going to reorient, and the most massive things will sink to the center of this new dynamical system. So you expect the two supermassive black holes to inspiral into the center of these galaxies, and in fact, there's a lot of work done on the time scale for these mergers, and there's a classic thing called the last parsec problem, which is how do you get the supermassive black holes to finally merge, because these supermassive black holes are really migrating to the center through their interaction with other things. So as they kick other things out, they merge in. This is one of the things that Lisa is definitely looking for, is the merger, but there should be an earlier stage where there should be binary supermassive black holes. And another place you can look for the evidence, or another line of evidence for the existence of binary supermassive black holes, are galaxies that have jets, two jets that are coming out, as if there was a merger, that there are two galaxies that came, and you see the jets from the two different supermassive black holes. So the short answer is yes, there should be binary supermassive black holes.
Okay, next question is a bit lengthy. I ask the person to phrase it shorter or talk verbally. So let's pass it for the moment. And the following one is by Vincent Smith. And he asks, since these stars are so close to the supermassive black hole, could a non-spherical shape of the black hole affect the orbit parameters?
It's so funny that I love that this question is being asked, because in fact, just yesterday I had a very long conversation with one of my collaborators about this idea. And he was reminding me of the history with the precession of Mercury, where there was a lot of debate about the geometry of the sun and whether or not the sun's oblate sun could create the precession that was seen. So yeah, it's an interesting question, and something that's useful to would be interesting to think about what else could cause this. So yes, and I'm thinking about this more recently than I would ordinarily have. I just started thinking about this yesterday.
All right. Waiting for the answer by John. Next one is Dimitri Kostunin. Are there other objects rotating around the supermassive black hole detected like planets or pulsars? And what are the properties of the detection, for example, the prospects of the detection, for example, by with radio telescopes?
Oh yeah, the pulsars is a particularly important one. So certainly there is an experiment. In fact, I should have mentioned that as another exciting project to try to find pulsars that are close to the center of the galaxy, because to have such an exquisite clock as a probe of the central potential would be really phenomenal. The challenge with finding pulsars at the Galactic Center is that there's smearing basically of the signal as it propagates from the center of the galaxy, because there's so much gas it has to go through. So far there has been no really close pulsar that would be effective enough for the timing discovered. But there is a massive effort underway to find such a thing. So that would be exciting. Planets are interesting to think about for fun. And it's interesting to think about what planets could survive in this environment, either tidally, maybe because these planets, in order to exist in a way that you would think naturally about a host star surrounded by a planet, most planets that exist in our own solar system would be easily tidally ripped off. So it's only, it would require a fairly close-in planet to survive. I don't know how you detect it in this environment today. In fact, that's another thing that's just worth mentioning. Today, we know we're thrilled to see these stars, but it's really, these are only the brightest stars. What limits us today at the center of the galaxy in terms of detection of objects is source confusion. So one of the reasons that we're so excited about getting to the 30-meter telescope, or that generation of telescopes, is that you should see so much more of the population when you get to that resolution. Today, a typical star, like a sun-like star, is just, you can't see it just because it's lost in the blur, the blurring of objects together, because the less bright stars are more dense, so you can't distinguish them. We call this source confusion. So if you think about an iceberg, we're just seeing the brightest stars. And I actually, the analogy I like to make here, well, the scientific analogy I like to make here is that it's like the planets. The first ones that we are detecting are truly surprising, but they're not the bulk of the population. So we might be seeing a lot of things that don't make sense only because we're looking at the brightest, rarest objects.
Okay. Then next one, finally, is John Apostolakis. And he says, first, hello and congratulations to you. And he has met you at Caltech as graduate student, so maybe you know him. And his question is, how would you expect to progress with understanding the population of young stars, studying the population, or trying to find a collision in progress?
A collision in progress. Well, one of the newer angles for us is actually to look at the brightness variations of these stars, as well as how not only it changes with brightness with a single wavelength, but also multiple wavelengths. And we're definitely seeing a lot of things that are very surprising. And one of the things that one could point to, but it would again, it's very speculative, are some of these really bizarre time variability caused by a merger, things that are in the process of mergers. I think it's a really interesting thing to think about, doing more detailed work in collaboration with people who are set up to do these merger calculations, to ask, what do they look like? What are the signatures and what is the time evolution? of these things. I think we're still in the early days of understanding that. But yeah, we're kind of excited about that. So thanks.
Okay, questions are coming and coming. So next one is by Maria Alandes Badillo, and she asks, you have spent more than 20 years to make a great discovery. This demonstrates how big science discoveries need time and resources that could be sustained over time. What are your thoughts regarding the support of big science projects?
Oh gosh, you know, if I had known at the beginning of this project it would take 25 years, I don't know. I don't think we would have gotten the telescope time. You know, we were only thinking 3 years to begin with. And in fact, that in itself is interesting and one of the topics I'm thinking a lot about, because to maintain 25 years of data and code in a context that really doesn't have the infrastructure, you know, it's all homegrown, and it's grown out of again, if you think you're doing something for 3 years, you write code and you do things in a different way. So this project is so different than projects where you know you're going to be doing this for a long time. In other words, we didn't set out. So we have the interesting challenge right now of trying to figure out how to create a stronger infrastructure around us, because there are all sorts of interesting things. And again, I definitely was not thinking about this 25 years ago. The project has gone from a very small team at UCLA. You know, I had one grad student and I had 2 collaborators at UCLA. And today it's a core collaboration. And by core, I mean people who are touching the data, who are evolving the code, that, you know, that aren't, I mean, there are a lot of people at UCLA, but there are people who are at other institutions. So Berkeley, Paris Observatory, in Granada, Spain. And so you have some interesting things that, I mean, interesting from an infrastructure point of view and a funding perspective and a collaboration perspective. You know, you really have different needs. You have to think about, well, how do you maintain, how do you understand? I mean, again, it's just such trivial stuff, but when you have to correct for this or create this mid-course, it's really different than creating it ahead of time, where you have a project where you've thought about, well, this is how we maintain a project that's big and long-term, versus this is how we have to put some better structure around something that's been growing. You know, it's the classic case of spaghetti code, or, you know, there's a need for more professionalism in the project. And in the US, this is a real problem. I mean, this is one of my biggest problems at the moment. So this is we face major funding problems, because, you know, the main way that science gets funded in the US for ground-based telescope work is through the National Science Foundation. But the National Science Foundation, while it funds research centers in many disciplines in physical sciences, the one it doesn't is astronomy. And that's because they invest in big telescopes. So it's an interesting structural, like funding structural problem, because of course, as we go to larger and larger telescopes, you actually need bigger and bigger collaborations. I mean, this is big science now. You need big teams to, you know, any individual is going to get a tiny amount of time on these large telescopes. So you better have these collaborations set up, and yet we're not really set up to fund them for this kind of work. So I spend my time, more time than I would like these days, trying to address this. Like, how do we set up the infrastructure, the people in Europe? I think there's I mean, again, maybe I'm talking out of ignorance, but certainly the how do you fund long-term senior people who are not faculty? That's critical for these long-term projects, and there's no good way of doing this. So the foundations in the US have been a big part of doing this, but there's no organized way of doing this. So I'm really great. I should say, I'm grateful for the NSF, and I'm grateful to the foundations that have stepped up to this. But in terms of continuing this, I'd say, along with my interest in the reference frame, the other thing that has to be figured out is how do you set up a research center that has some stability to keep this going? Because we actually now have, over the last 5 years, we've had somebody from information sciences studying us because she got really interested in asking, how do these long-term projects survive? And one of the things that we've learned from this collaboration with her, so she had a grad student do a PhD looking at how have we survived. And it's just been interesting to have it articulated, because of course when you're experiencing it, you don't necessarily have you just deal with the latest put out fires as you go along, and to have somebody looking at how you've managed this, it was really interesting. And the conclusion, which makes a lot of sense to me, is the fact that we've been so interested in continually evolving the methodology and how we do things is how we've succeeded, because we're constantly going back into the code. In other words, it creates that knowledge. It sustains the knowledge, and we keep reanalyzing the data, which means it sustains the data. So I'd say, I mean, it's a little bit of a joke in the group that, every 5 years we sort of take a serious overhaul and reanalyze everything, but it means that you have to think about, well, where is all the data, and can you put it on a medium that's actually the newest medium instead of the old, we started with exabyte tapes. If the raw data were still on it, it would have died by now. So it's interesting to think about the fact that we're interested in methodology is what's actually been key to the sustenance of the whole endeavor over time. But those are the things that are on my mind with respect to this question.
Okay, and one more question. What about by Ivan Dimitri? What about observations of the same region in different energy bands?
Oh, yes. In fact, one of the things that has been so wonderful about moving from speckle imaging to adaptive optics is we've been able to move out of one energy band. And so I'm taking your a very narrow starting point. So we've moved from 2 microns to be able to see at least 1 to 5. So that gives you more information in terms of the characteristics of stars. The center of the galaxy is only accessible at the moment because of all the dust in 3 basic energy bands. So the infrared, to take a more a larger scale take on the question. So you can see it at X-ray wavelengths and you can see it at radio wavelengths. So each one picks up different physical processes. The area or the part of this project, which I've actually given short shrift to in this presentation, where that multiplicity or the multi-messenger aspect of the work that's benefited from the most is looking at black hole accretion physics. So looking at the time variations and the colors and the color variations. So there's a lot of data that's out there that's been used to try to understand the accretion properties of the black hole. I would say it's just messier physics. So in terms of how much we've been able to learn or say over 20 years in this arena, it's been, I mean, there's a reason why I give it short shrift, like the message isn't as clear. So it's variable. It's but I think as we make more and more precision measurements, there's some interesting things that might be emerging in terms of our ability to understand what causes some of this variation. But you're really talking about much more microphysics, more thinking about the smallest scale of turbulence in the plasma accretion flow, or looking for maybe microlensing of flux tubes by the black hole. I mean, these are the things that one might be able to do, but it's so much harder. I mean, this compared to this gravitational stuff, which is so nice and clean.
Okay, there are no further questions, except I have a final question. You achieved this tremendous progress within the last 25 years, increasing the resolution by an incredible factor. If you make a wild guess, what would be possible, say, within the next 25 years? I mean, can one, for example, make precision measurements of fine structure at the event horizon or something like this?
Well, I think, this is where I think we're in a moment where there's so much that the next 20 years holds. I mean, so I hope that we'll be at the point where we're getting results from the 30-meter telescope, European extremely large telescopes, and there'll be tremendous progress in the sense that it's a D to the fourth game. So you're getting, you know, a factor of 80 by going to that regime. So that's exciting. I certainly hope that it'll be interesting to see if we get LISA on that time scale. And then, of course, the Event Horizon Telescope and progress with the radio telescopes. So and their ability to detect pulsars. So I think the next 20 years, there's so much technical progress that's being made and so much enthusiasm for it that I think it'll be an interesting period, equally interesting.
Okay, thank you. Yeah, I think that can be expected from this field for sure. So thank you very much for this very inspiring and lively talk and discussion. There are no other questions, so let me thank you again for all the people who have, well, in lieu of all the people who have been listening, either via Zoom or by streaming. And well, if once Corona crisis is over and you happen to be in the region, then please come by again and have a visit.
Thanks so much. It's been delightful, and I certainly hope to take you up on that offer.